Hello students. So, this is lecture number 30 and we are going to study some case studies and examples based on the special types of LPPs, and I will also give you some questions which are short answer type and then I will give you the solution to that as well. So, let us begin. Here is the first question which says that we have supposed to determine the ideal and the efficient solutions of the following multi-objective linear programming problem. Now, as you know that this is a case of a multi-objective optimization problem where there are two types of solutions, that is the ideal solutions and the efficient solutions. So, here we have two objective functions which are to be maximized. First one is 5x1 plus 4x2 and the second one is 3x1 minus 2x2. They are subject to the constraints x1 plus 2 times x2 less than or equal to 4 and minus x1 plus x2 less than or equal to 1, and this is subject to also the constraints, that is x1 and x2 should be greater than or equal to 0. So, let us look at the solution of the problem. So, let us first of all look at the feasible region. So, the feasible region is shown like this. We need to write down the constraints like this. So, the two functions are maximize f1 is equal to 5x1 plus 4x2 and the second one is maximize f2 is equal to 3x1 minus 2x2 subject to the constraint x1 plus 2x2 less than or equal to 4 minus x1 plus x2 is less than or equal to 1. Now, I hope you remember how do we plot these constraints. So, the first constraint passes through the point 0, 2 and 4, 0, and the second constraint it passes through the points 0, 1 and minus 1, 0. So, let us plot these 2 points. So, 0, 2 is here and 4, 0 is here. So, we need to draw a straight line passing through these 2 points, and as per the less than equal to sign of the constraint, it means that the feasible region is below the line. Similarly, the second constraint should pass through 0, 1, that is this point, and minus 1, 0 this point. So, therefore, we need to draw a straight line which passes through these 2 points, and as per the less than equal to sign, the feasible region is below the line. So, this is our feasible region. It is indicated by O. So, let us write down the feasible region 0, 0. This is the point O. Then the point A, which is given by 4, 0, and the third point is the point B. This point is the intersection of the 2 lines, and you can verify that the intersection of these 2 lines is given by 2 by 3, 5 by 3. This you can obtain by solving the 2 equations. And finally, the point C, which is given by 0, 1. So, these are the 4 points which are showing the feasible region. Next, let us look at the two objective functions. So, we have to maximize f1 which is given by 5x1 plus 4x2, and similarly the second objective function maximize of f2 is equal to 3x1 minus 2x2. So, just as we do for the single variable problem, exactly in the same way we will evaluate the objective function at each of these points, both the objective functions. So, the first 0 0 will give you the f1 value as 0, the A point will give you 20, the B point will give you 10 and C will give you 4. So, what do we find? Since we have to maximize it, so therefore, the maximization occurs at the point A, because the objective function is maximum over here. Similarly, in the second objective function, the value of the objective function at O is 0, at A is 12, at B is minus 4 by 3, and at C it is minus 2. So, this tells us that if you look at all these values, you find 12 is the largest, and since we have to maximize it. So, this tells us that again the optimum solution is obtained at the point A given by 1, 0. So, therefore, the problem was to find out the points at which we have the ideal solution and the efficient solutions. So, since you can see that A is the point where you have a ideal solution, because both the objective functions are giving us the maximum value or the optimum value corresponding to each of the objective functions. However, the other points, that is O, B and C, they are giving us the efficient solutions. So, A, the point A. So, therefore, what do we see that A, the point A is giving us the ideal solution, because it is maximizing both the objective functions. So, therefore, A is the ideal solution, whereas the remaining points, that is O, B and C, they are giving us the efficient solutions. So, that is the way to solve a multi-objective optimization problem. Now, the second problem that I am going to solve is about the integer programming problem using the branch and bound method. So, here we have the problem, it is a two variable problem. We have to maximize z given by x1 plus x2 subject to the condition 3x1 plus 2x2 less than or equal to 5 and x2 is less than or equal to 2 and x1 and x2 greater than or equal to 0, and both should be integers. So, let us see how to solve this problem. So, again we need to plot the feasible region to understand how the feasible region looks like. So, on the x axis we have x1 and on the y axis we have x2. So, let us plot the values 0, 1 and 2, 0, 1 and 2. The problem that is given to us is maximize z is equal to x1 plus x2 subject to the condition 3x1 plus 2x2 less than or equal to 5, x2 is less than or equal to 2, x1 and x2 greater than or equal to 0. So, first of all we will solve the LP0. Remember what we have to write it in the form of a tree, that is the base, that is the LP0, and we need to find out what is its solution. So, therefore, we need to first plot this constraint, and as before x1, if x1 is 0, then x2 is to be obtained like this, and similarly I will just leave this as an exercise. So, we will plot this like this. There are 2 points over here, this point and this point. So, they have to be joined together, and obviously because of the inequality constraint, the region is below the line. Similarly, the second constraint, that is x2 is less than or equal to 2. So, this is also below the line, and now we have the feasible region as O, A, B and C. So, therefore, what we have to see the value. So, O is given by 0, 0 and the value of Z is x1 plus x2. So, it is 0. A is the point 0, 1, it is giving objective function value 2. Similarly, B is the point 1 by 3, 2, which is giving 7 by 3, and C is the point 5 by 3, 0, which gives us 5 by 3. So, this means that since we have to maximize the problem, so the maximum occurs at the point B. This is our maximum. So, therefore, our LP0 is giving us the solution 1 by 3, 2 with objective function value 7 by 3. Now, since the first component x1 is not integer, therefore, we need to do the bifurcation like this. So, the bifurcation is as follows: x1 should be less than equal to 0 and x1 should be greater than or equal to 1. And when we solve these two conditions with these two LPs, so the feasible region for the LP 01 is given by the line OA, line segment OA. So, here is the line segment OA, and as you know that there are only 2 points, the line segment OA, it constitutes of 2 points 0, 0 having an objective function value 0 and A has the objective function value 0, 1, which gives us 2, and the maximum value is obtained at the point A. So, A is the solution. So, therefore, for LP01 the solution is 0, 2 and Z is equal to 2. Similarly, we will solve the other constraint, which is LP02. Now, LP02 is having the feasible region as EDC. So, this is LP02 has this EDC. The value of E is 1, 0, which gives us 1. D is 1, 0, which gives us again 1, 1, which gives us 1, and E is 5 by 3, 0, which gives us 5 by 3. So, this tells us that the solution is again at the point D. So, therefore, the solution is 1, 1 with objective function value 2. So, therefore, what do we conclude? We conclude that all the nodes that is LP01 and LP02 have obtained integer solutions, and therefore, we can conclude that the problem has been solved. So, we find that both these solutions are giving us the objective function value as 2. So, therefore, it means that the solution is at both these 2 points. Next, let us solve another example 3. This is a transportation problem. So, the problem says that wheat is produced at Punjab, Haryana, UP is to be transported to the cities Delhi, Mumbai, Chennai and Kolkata using the following cost. So, this is cost is given to us. We have to use the northwest corner rule to determine the transportation cost and compare our results with that obtained by the least cost method. Now, as you remember that in the transportation problem I told you that it is you have to first find a BFS, and there are 3 ways to find out the BFS, that is the least cost method, the northwest corner rule and the Vogel's approximation method. So, once you get the initial BFS, then you have to apply the test for optimality. So, in this exercise we are supposed to obtain the BFS using the northwest corner rule and compare our result with the least cost method. Now, the data that has been given to us is as follows. It is shown here in this table. At the top we have Delhi, Mumbai, Chennai, Kolkata, and at the left hand side is the Punjab, Haryana and UP. The data that has been given to us is 20, 50, 40, 60, 16, 30, 45, 40, 14, 8, 30 and 15. Also, the data says that the supply at the sources, that is the Punjab, Haryana and UP is given, that is 9, 7 and 5, and the demand is also given as 8, 5, 4 and 4. So, we have now to solve this problem, that is we have to obtain its BFS using the northwest corner rule. So, how to first of all we need to check whether this is a balanced problem or not. So, we need to add up 8 plus 5 is 13 and 4 and 4. So, how much is that, and how much is 9, 7 and 5. So, this is 21. Both these give us the value as 21, which means that this is a balanced transportation problem. So, in order to implement the northwest corner rule, first we have to look at 8 and 9. 8 is the demand in Delhi and the supply in 9. So, the minimum of the 2 has to be chosen. So, minimum is 8. So, therefore, 8 will come over here and this is striked off. From 9 we have to minus 8. So, this gives us 1. Then we move to the next cell, that is this cell, Mumbai, Punjab. Now, this cell tells us that we have to compare 1 and 5. So, out of 1 and 5 minimum is 1. So, therefore, 1 will come in this cell and this 1 will be deleted and 5 minus 1 will give us 4. Then we have to come to the bottom cell over here, that is the Haryana and Mumbai. So, we compare the value 4 and 7 which gives us 4. So, therefore, 4 comes here and this is satisfied and 7 minus 4 is 3. Then we compare 3 and 4, this 3 and this 4. So, this tells us that minimum is 3. So, this is satisfied and 4 minus 3 is 1. So, here this is 1 and this is 1. Then that means we have to compare with 1 and 5, and 1 and 5 means 1. So, this is 5 minus 1, that is 4, and now we are left with 4 supply and 4 demand, and therefore, both will be satisfied and this will come over here. So, this means that using the northwest corner rule, the cost is as follows: 20 into 8 plus 50 into 1 and 30 into 4 plus 45 into 1 plus 30 into 1 plus 15 into 4, and if you calculate this you should get 505. So, this is the cost that you get using the northwest corner rule. Now, in the problem it says that we have to compare our results with the least cost method. So, this I will leave as an exercise for you to carry out, and in fact you should also calculate using the third method, that is the Vogel's approximation method. So, now we come to the quiz of this topic. So, here are some questions and I want you to write down the answers in your notebooks. So, the first question says the feasible region of an integer programming problem is non-convex, true or false? Feasible region of an integer programming problem is non-convex, true or false? Number 2, in an integer programming problem, a node which is containing all integer solutions is called a dash node. In an integer programming problem, a node which is containing all integer solutions is called as a dash node. Question number 3, in an integer programming problem, a node which is infeasible is called as a dash node. In an integer programming problem, a node which is infeasible is called as a dash node. Question number 4, the solution of a goal programming problem is always an integer solution, true or false? The solution of a goal programming problem is always an integer solution, true or false? Question number 5, in a goal programming problem, to achieve the goal as closely as possible, the objective should be to minimize the dash from the goal. In a goal programming problem, to achieve the goal as closely as possible, the objective should be to minimize the dash from the goal. Question number 6, branch and bound method is an efficient method to solve the goal programming problem, true or false? The branch and bound method is an efficient method to solve the goal programming problem, true or false? Question number 7, Gomory's cutting plane method is an efficient method to solve a goal programming problem, true or false? Gomory's cutting plane method is an efficient method to solve a goal programming problem, true or false? Question number 8, if x0 is a unique minimal point for any of the objective functions, say Fix in a multi-objective optimization problem, then x0 is an efficient solution of the problem, but the converse is not true. True or false? If x0 is a unique minimal point for any of the objective function, say Fix, in a multi-objective optimization problem, then x0 is an efficient solution of the problem, but the converse is not true. True or false? Question number 9. Richard Bellman's principle of optimality states the dash. Richard Bellman's principle of optimality states that dash. You have to write the principle. Question number 10. Dynamic programming is also called as a recursive programming problem. True or false? Dynamic programming problem is also called as a recursive programming problem. True or false? Question number 11. A transportation problem is a special type of a linear programming problem. True or false? A transportation problem is a special type of a linear programming problem. True or false? Question number 12. In a balanced transportation problem of 4 origins and 5 destinations, the number of linearly independent constraint equations is dash. In a balanced transportation problem of 4 origins and 5 destinations, the number of linearly independent constraint equations is dash. Question number 13. An assignment problem is a special case of a transportation problem. True or false? An assignment problem is a special case of a transportation problem. True or false? Question number 14. In an assignment problem, the number of persons available for carrying out jobs must be the same as the number of jobs. True or false? In an assignment problem, the number of persons available for carrying out jobs must be same as the number of jobs. True or false? Question number 15. In the solution of an assignment problem, the optimum solution is indicated if the minimum number of horizontal and vertical lines which need to be drawn to cover all zeros in the assignment table is the same as the number of jobs. True or false? In the solution of an assignment problem, the optimal solution is indicated if the minimum number of horizontal and vertical lines which need to be drawn to cover all the zeros in the assignment table is the same as the number of jobs. True or false? So, I hope everybody has written the answers. Now, let us look at the answers. I will give you the answers to each of the questions. So, question number 1, the feasible region of an integer programming problem is non-convex. The answer is true. Question number 2, in an integer programming problem, a node which is containing all integer solutions is called as a fathomed node. Question number 3. In an integer programming problem, a node which is infeasible is called as a pruned node. Question number 4. The solution of a goal programming problem is always an integer programming problem, is an integer solution. So, the answer is false. Question number 5. In a goal programming problem, to achieve the goal as closely as possible, the objective should be to minimize the deviations from the goal. Question number 6. Branch and bound method is an efficient method to solve the goal programming problem. False. Question number 7. Gomory's cutting plane method is an efficient solution to solve a goal programming problem. False. Question number 8. If x0 is a unique minimal point for any of the objective functions, say f(I)x in a multi-objective problem, then x0 is an efficient solution of the problem, but the converse is not true. The answer is true. This is the theorem that we have learnt. Question number 9. The Richard Bellman's principle of optimality states that an optimal policy has the property that whatever the initial state and the initial decisions are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. Question number 10. Dynamic programming is also called as a recursive programming problem. The answer is true. Question number 11. A transportation problem is a special type of a linear programming problem. Answer is true. Question number 12. In a balanced transportation problem of 4 origins and 5 destinations, the number of linearly independent constraint equations is 8. So, how did this come? It came because it is n plus m minus 1. So, 4 plus 5 is 9. So, minus 1 is 8. Question number 13. An assignment problem is a special case of a transportation problem. The answer is true. Question number 14. In an assignment problem, the number of persons available for carrying out the jobs must be the same as the number of jobs. Answer is true. Question number 15. In the solution of an assignment problem, the optimal solution is indicated if the minimum number of horizontal and vertical lines which need to be drawn to cover all the zeros in the assignment table is the same as the number of jobs. Answer is true. So, I hope you have evaluated your attempt to this quiz. So, with this we come to an end of this lecture. Thank you.